All right, let's do some more practice on our free response. Today I'm going to be working the 2008 released practice exam, the international practice exam. I'm going to be working the first 3 free response questions. So it starts with the rate at which raw sewage enters a treatment tank, and that's going to be EFT, is the rate in. Treated sewage is removed from the tank at the constant rate of 645 gallons per hour. So that means rate out is going to be 645. All right, so how many gallons of sewage enter the treatment tank during 0 to 4? Well, we're just going to integrate the rate in to get the total in. So that's going to be the integral from 0 to 4 of EFT dt. And then I'm going to, it's very important that we report the integral that we're running through the calculator. We don't have to write out what EFT is. We don't have to write out the 850 plus 715 cosine of pi t squared over 9. We just have to write EFT dt to let the reader know what we're doing here. And I'm going to type in 850 into, I'm going to type this thing into y1 so that I could use it again. And then that definitely looks like a time for a fraction bar, pi t squared over 9. That's not a 9. All right, and I've got that. And while I'm at it, I might put 645 into y2, So I'm going to say integral from 0 to 4 of, I put EFT in y1 with respect to time, and that's going to be 3,981. To the nearest gallon, that's 3,981 gallons. Okay. And then for t between 0 and 4, at what time t is the amount of sewage in the treatment tank greatest? This is an absolute maximum on a closed interval. Okay, and I'm gonna say, all right, well that means that I need to, amount of sewage in the tank, that's not a function we've defined. Okay, we need to write that. Okay, so the amount of sewage at time t is going to start out empty. Okay, so it's going to be 0 plus the integral from time 0 up to time t of rate in minus rate out dt. Okay, now I know, not dt. That's why I left that blank, right? Because we can't use t as the independent variable like, hey, here's how far you integrate, and this is the variable you integrate with respect to. So we just choose some other variable like, I don't know, w. And then that's our function. Okay, you could use s or, really anything besides probably t, capital A, capital E, right? Everything else is good. So this is the total function, right? I know that a of 0 equals 0 because the tank started empty. A of 4, well, I'm going to have to do that, but I already know it's 3,981. I might actually go in and type in the same thing, minus 645 in the integrand, integrate rate in minus rate out to get the total in minus total out, and that'll be 1,401. Okay, but then we also need to know when are the times when a prime is equal to 0. So first we're going to take a prime, and that's where we'll throw t in for the dummy variable wherever we see it in the integrand. So that's just going to be e of t minus 645. Also, you could say that the net rate of change is rate in minus rate out, right? However you see it. Okay, I need to know where this is equal to 0. So what I'm probably going to do is I'm going to graph this and see where it's equal to 0. So I don't have to take the window all the way up to y equals 645. We don't want to do that. Okay, what we're going to do, we're going to go over here. I'm going to clear that out. And what I'm going to do instead is I'm going to subtract 645. I'm going to graph this on the interval 0 to 4. I'm going to need some wide, width so I can see it crossing the axis. But that should be good. It should happen hopefully just once is what I'm hoping for. But I'm ready. Yep, it happened twice. It's all right. I need to check both of them, right? That's what I've told you all year, is that when computing an absolute maximum, the first one's between 2 and 3. An absolute maximum or an absolute minimum, you have to just check all the critical points. The amount of writing that you have to do to exclude a critical point, you're faster to just check all the critical points. So I've got here 1. Time equals, and I'm going to say a prime of t equals 0 when t is equal to 2 and I'm going to 309 3428. Okay. And I'm going to copy all the decimals because I don't know how many I need. Okay, the left bound is going to be 3, the right bound is going to be 4 when I find the second 0, and then that will be t equals 3.5590639. Okay, now what I'm going to do is I'm going to quit, and I'm going to go back to this thing, and I'm going to just kind of manipulate the upper bound, right? So I need to check the amount at 2.230933428, and I'll get 195 gallons. Okay. What was it? 195. Okay, and then I'm going to compute the same thing at time t equals 3.5590639, and that's going to be, let's see, okay, enter that again. Yeah, that'll be 3.5590639. We didn't have that extra decimal. What? Wait a second. Oh, okay, I know what happened. Okay, I need to be careful. I need to go back and change. Oh, man, this was... Yeah, Y1 has the minus 645 in it. Okay, that's troublesome. So I need to go back up to this one, kill off the negative 645. I was like, man. Okay, yeah, that seemed like a really low amount of sewage. Yeah, so that's 1,634. Oh, boy, that was a close call. 1,634, and then the amount at the time right before 4, like I knew it can't really go from negative to positive 1,400. There had to be an explosion of raw sewage, you know, like that would not be, that's not realistic. So I'm going to go up here, I'm going to get rid of that 645 thing, that's not necessary, and then I'll have 1,229. And now I'm going to conclude the maximum amount is, there it is, 1,634 gallons. Okay. All right, the cost of treating the raw sewage that enters the tank at time t is 0.15 minus 0.02 t dollars per gallon. Okay, to the nearest dollar, what is the total cost of treating all the sewage that enters the tank during the time interval 0 to 4? I have not given this problem in quite a while. Okay, the thing about this one is, I think it's pretty easy to see that I need to integrate, right? It's going to be an integral, okay? And it's going to be related to the integral of E of t, because it's the sewage that enters the tank at time t. But, you know, I don't know, some people just can see that it's supposed to be this thing times E of t, but I think that on a unit conversion level, I can show you something that'll, you know, make it make some sense. Okay, so we've got E of t, and that's gallons per hour, I believe. Yeah, right there it says it, gallons per hour. Okay, and then we're going to, I think, multiply by this other function, 0.15 minus 0.02t, and that's dollars per gallon. Is going to come out to E of t times 0.15 minus 0.02t dollars per hour, so I could integrate this function with respect to time and get a total number of dollars. Okay, so that's why I'm going to be integrating from 0 to 4, E of t multiplied by this 0.15 minus 0.02t dt. Okay. Or you could think about what you're adding up in your integral. You're just adding up a bunch of things together. It's an amount of sewage that entered at, you know, in an instant times the amount of money that it costs to treat that amount of sewage. And so, you know, in that instant, and that's going to be these two things at an instant time t. Okay, so that's what I'm going to do. I think that's, well, that's all the explanation I've got. Okay, I'm going to go in here and I'm going to get rid of that 645. Okay. In retrospect, I probably should have only put in the negative 645 for when I was graphing, and then switched it back and had y1, y2. But, you know, I did what I did, so can't go back now. 0 to 4 of E of t is y1 multiplied by 0.15 minus 0.02t with respect to time. And then that's going to be 6,000, let's see, to the nearest dollar, it said. So that'll be $6,260. Okay, and nominal. A particle moving along a curve in the xy plane has position x and y at time t when they give us the derivatives of x and y. Okay? At time t equals 3, the particle is at 0.54. Find the speed of the particle at time t equals 3. All right. Well, speed is going to be x prime of 3 squared plus y prime of 3 squared. That's one of the formulas we just need to know. Okay? And that's just going to be an issue of, I mean, I think because it's a calculator, I'm going to probably go in and just type these into y1 and y2, because I know I'm going to need to use them eventually. So I'm going to put in a fraction bar, 6 divided by t minus 3 to the 1/3 power. And this is going to be t e to the negative t. Okay. And then I'm going to say, all right, that's basically, I'm going to take the square root of y1 of 3 squared plus y2 of 3 squared. I'm going to get 1.011. Okay, that's justification enough. That's what I'm plugging into my calculator, right? It's very important that we tell the reader what we're plugging into the calculator. Write an equation for the line tangent to the path of the particle at t equals 3. All right, so I'm going to need a point. That's going to be 5, 4. It gave me that up here. And my slope is dy dx equals y prime of 3 divided by x prime of 3. Okay, I've got y prime and y2, so I'm going to need to put y2 on top, but this is still something I can do, so that's going to be y2 of 3 divided by y1 of 3. Okay, a mistake I saw people making when we took a free response practice test was that they were computing these separately and then putting them as a ratio, and they rounded each of the values on top and bottom to 3 decimals. And then it turned out when you actually divided those 3 decimal numbers, you were no longer accurate to the 3rd decimal place. So I just really want to encourage you to be careful about early rounding. Right now I'm taking the time. There might be another time in this problem set where I'm going to encourage you to do the same thing, but it's something you need to be aware of. Okay, now that I've got a slope, now I'm able to round to 3 decimal places. Okay, and now that I've got a point and a slope, my equation for the tangent line is y minus 4 equals negative 0.149 times x minus 5. Now, if for some reason you did this and you were, you know, the time had expired on the calculator section and but you finished all the no calculator problems, you could go back to this one and you could just write 3e to the negative 3 divided by 6 over 3 minus 3 to the 1/3 power for this slope. Right, because that's just a number, it's equivalent to that, and you know, that's one of the places where we could still easily recover credit if we had done it wrong and we were coming back on it, but we didn't have a calculator for the calculator problems. Is there a time t at which the particle is farthest to the right? If yes, explain why. Oh, okay, and this is t greater than 0. Okay, so what we're going to need to do is look at dx dt. And I feel like if we can kind of provide some sort of narrative about dx dt, we'll be able to say yes or no. Okay, so dx dt, let's graph this. Let's just not graph the other one so it's not distracting us. We're just going to be looking at the blue line from 0 to, let's just go to 10. I bet all of the action is going to happen there. But I'm going to want the full wide picture, so I'm going to do this. Oh, interesting. Okay. And then let's think about, well, actually, no, I think I'm going to say dx dt is positive until t equals 2. and then dx dt is less than 0. Let's see if that's going to always be true, because if we take a number, yes, the bigger that t gets, the smaller that 6 over t gets. And I basically have -3 to the 1/3 power. So we're going to be approaching a horizontal asymptote of the cubed root of -3. Okay? And so then dx dt is less than 0 for all t greater than 2. Okay? The limit as t approaches infinity of dx dt, I don't know if this is really necessary. That's going to be the cubed root of -3, which, I mean, I'm just really hammering home the fact that I really understand that dx dt is always negative after t equals 2. Okay? So if dx dt is positive, we're moving to the right, and then we move back to the left. So yes, farthest to the right at t equals 2. Okay, then we're going to need to find the position, or the x-coordinate of the position of the particle at time t equals 2. So that means I need to find x of 2. Well, I already have x of 0. I've kind of forgotten what it is. Looks like x of 0 is 5. No, x of 3. Plus the integral from a to b, so that's 3 to 2, of x prime of t dt. Okay, that's a job for the calculator. So that's going to be 5 plus the integral from 3 to 2 of x prime. Okay, that's the 6 over x minus 3. Just going to triple check that. Yeah. Okay, so that's y1. And then it's going to give me my answer, 5.792. All right. Describe the behavior of the path of the particle as t increases without bound. Oh, good for me. I found dx dt has a finite limit. Let's look at dy dt. That's equal to t e to the -t, which I could also write as t over e to the t, right? I'm going to say that the limit as t approaches infinity of dy dt is going to equal 0. Pardon me, I didn't realize that was not on screen. Okay. We found that the limit of dx dt as t went to, that's t increases without bound. That means t goes to infinity. That was the cubed root of -3. Okay, so it appears to me that eventually y is going to stop changing, right? Because dy dt goes towards 0. Okay, and then x is still going to the left. So you could say it moves to the left on a, increasingly horizontal line. You could say it's approaching a horizontal asymptote, I think would be good. I'm going to look up the scoring guidelines for this one real quick and try to describe to you what it's saying. I'm going to say that approaches a horizontal asymptote is one thing I'm going to say. But because this is not a very typical AP Calculus problem type, I'm going to say more. I'm going to make sure I'm only saying things that are true, but I don't know what, because it's not one of those like very obvious problem types like, oh, find the absolute maximum of the amount of raw sewage, or the amount of sewage. And we get those types of problems every year. We know exactly what to do. With this one, I'm going to have to say some more things. So, all right, approaches a horizontal asymptote. Continues moving left. I don't really have anything else to say. I think I'm going to stop there, and I'm going to pull up the scoring guidelines. Okay, interesting. So this was 2 points. One was for the behavior of x, and one was for the behavior of y. And so I'll read you what they said. it says, since limit as t approaches infinity of dx dt is negative 3 to the 1/3 power, and limit of dy dt as t approaches infinity is equal to 0, the particle will continue moving farther to the left while approaching a horizontal asymptote. Okay, I think I hit that. So I'm just going to, you know what, while I'm at it, I'm just going to show you how this one was scored. This was 1 point for the behavior of x and 1 point for the behavior of y, so I think you probably would have gotten the points for these two things. Over here, it was 1 point for yes with explanation, which is probably like yes with it's positive and then it's negative. Okay. The second point on this is worth 4 points. Is identifying t equals 2 as a candidate. The third one is the integral for x of 2. And the fourth one is for the x coordinate. Okay, so that's the fourth point. If I flip back over here, I think the first one was 1 point for the answer, yeah, and then 1 point for the slope, and 1 for the equation of the tangent line. So slope and the equation of the tangent line. Okay, and that's how that one was scored. Okay, I'm not going to go in and do that for all of them, just for the ones where we have something like really not standard happening. All right, third one. This one you're going to not be able to use a calculator on, I think, unless let's look real quick. I know that at a certain point you are allowed to use a calculator on the first 3. So I'm going to work this one without a calculator. And I think that should be fine. Estimate the instantaneous rate of change. That's going to be do rise over run on the table. Temperature of the oven is changing at time t equals 10. Okay, show the computations that lead to my answer. Okay, that's going to be me showing that I'm computing h of 12 minus h of 8 divided by 12 minus 8. Okay, that's the computations that lead to my answer. And I might say my approximation for h prime of 10. And I'm going to say this is equal to h of 12 minus h of 8 over 12 minus 8 units of h divided by units of time. So degrees Celsius per minute. Okay. And then we don't need to simplify this, right? No need. Write an integral expression in terms of h, okay, for the average temperature of the oven between 0 and 16. Okay, well, an average value of h is 1 over 16 minus 0 times the integral from 0 to 16 of h of t dt. It's the average value integral they're asking for. Then we're going to estimate the average temperature of the oven using a left Riemann sum with 4 subintervals of equal length, which happens to be exactly what they gave me on the table. Okay. So if I'm doing a left Riemann sum, okay, I'm going to take the 1 over 16, and I'm going to factor it out, and then I'm just going to do my left Riemann sum, and I'm not going to be simplifying it, right, unless I need to use it later. All right, so a left Riemann sum, I'm going to multiply width by representative height, and the representative height comes on the left side of the interval. Okay, so 0 to 4 has a width of 4. Representative height is 65. Okay, 4 subintervals of equal width, that means it's always going to be 4 times something. And it's 4 subintervals, so there's going to be 4 4s. Okay. And then in these numbers, I'm going to take my height from my representative from each subinterval, which will be the left endpoint, which will be 68, 73, and 80. Okay, done, right? Don't simplify. Don't, especially if it's no calculator, there's no point in wasting the time to do the arithmetic and risking the arithmetic error. I don't want you to do either of those things. So, is my approximation in part B an underestimate or an overestimate for the average temperature? Okay, it must be that they told me something about whether h was increasing or decreasing. It did definitely seem like it was increasing. Yes. H is increasing. That's going to be useful. And it's continuous, so that means that we could, it was integrable. I don't think you need to say that. Okay. H is increasing. Okay. Then, so I'm going to draw a picture of an increasing function. Now, remember, your picture gets you no credit as far as like your reasoning or anything, or your answer. So, and you can't appeal to the picture either. But it will help you decide whether it's an overestimate or an underestimate, right? And so my advice is always subdivide into 2 subintervals, right? So you can really see it. So it's really a lot of error, okay? And then we use the left edge of each subinterval, okay? So that's my height, and it's going to be an underestimate. Okay, that's my left side, that's my height. Okay, it's an underestimate. H is increasing, so a left Riemann sum underestimates. I'm going to say, okay, they did mention the thing about dividing by 16. Okay, so they were like, hey, you ran a left Riemann sum on an increasing function, therefore it's going to be an underestimate, and dividing by 16 won't change anything. So I'm just going to say it underestimates the integral, or 1 over 16 times the integral from 0 to 16 of h of t dt. Because it's true. All right, then are the data in the table consistent with, or do they contradict the claim that the temperature of the oven is increasing at an increasing rate? Okay, I'm glad this is on there. There was one of on the practice test that we took where there was something about it, increasing or decreasing rate. Okay, so the rate is h prime of t. Okay, so they're basically asking us, is the rate increasing or is the rate decreasing? And we know that the rate is h prime of t, is the derivative. Okay? So we know that if we want to determine if f of x is increasing, we take the derivative of f and we check its sign. So that's what we're going to do to h prime. So I'm going to say h double prime of t, positive or negative? Okay. So I'm going to go over here. And I'm going to, I guess I'm going to just copy the table. What I want to do is I want to take the first and second differences and then kind of, look based on that. But yeah, I'm going to just copy the table, I guess. All right, so basically our, especially because they're evenly spaced, I could find the increase and divide by 4, but I'm just going to say plus 3, plus 5, plus 7, plus 10. Okay, since now I don't know, this is not a typical problem type, so again I'm going to look up there. I'm going to say the maybe, yeah, I think I'm going to say that the slopes, yeah, I'm going to find that, I don't know what I'm going to do. I'm going to say the slopes of these things are going to be increasing. Okay, so the slope from t equals 0 to t equals 4 is going to be about 3/4. Okay, then from t equals 4 to t equals 8, that slope's going to be 5/4. Then from t equals 8 to t equals 12, then that would be 7/4. And the slope from t equals 12 to t equals 16 is 10/4. Okay, because the slopes are increasing, I'm going to say that's evidence that h prime is increasing, and so it would be consistent. Okay. Now, let's, yeah, that's it for this problem set, right? Oh, okay, well, there's 2D attached to this maybe on your booklet, but I'm going to record that as a separate video because I've got a class about to come in. But let's look at the scoring guidelines, starting from part D and then moving backwards, okay, because this one was also kind of a strange one. All right, part D. All right, this is the response that they gave. if a continuous function is increasing at an increasing rate, then the slopes of the secant lines of the graph of the function are increasing. The slopes of the, okay, this is a good sign. The slopes of the secant lines for the 4 intervals in the table are 3/4, 5/4, 7/4, and 10/4 respectively. That was like a whole paragraph. Then they have like an indented paragraph. I guess it's like, that's going to be the conclusion. Since the slopes are increasing, the data are consistent with the claim. Or you could invoke the mean value theorem. Yeah, that h prime of, kind of these various c values between 0 and 4, 4 and 8, 8 and 12, 12 and 16, those are increasing. I think, well, this would have gotten the credit. It was 3 points, one for considering the slope of 4 secant lines, one for the explanation, one for the, saying that the conclusion is consistent with the explanation. Okay. Then part C is 1 point for the answer with the correct reasoning. Okay. Over here, 3 points, one for the average value expression. I'm looking. Okay, yeah, okay. 1 point for the average value expression right here. 1 point for a left Riemann sum. That means I think 4 out of 6 of these numbers are correct. And then 1 for the answer, which is, all of these numbers being correct. And then over here, 1 point for doing any kind of difference quotient, and then 1 point for the correct answer with the units. So if you messed up the units, if you did run over rise, you're going to get 1 out of 2, which is pretty generous. Hey, but I think that's all I've got for you for this video. Thanks for watching.